Good afternoon, everyone. I hope all of you are doing well in this situation. So, and be safe and try to follow all the protocols. Anyway, today we are going to perform that the experiment name is the C common mode emitter amplifier. So actually, till date we have studied about different modes of BJT, means bipolar junction transistor. So today we will study a direct application of that. So we can, as we have discussed already, that we can use this transistor in as a amplifier as well as in as a switch. So basically, if you can recall that a transistor is having three different region. One is cutoff region, active region, and saturation region. So in order to make sure that the transistor is working, we have to keep a transistor in active mode, active region, until unless any special requirement of saturation or cutoff. If it is required for particular case, then it is okay. Otherwise, it should be in active mode. I mean, active region, where we can use it as a amplifier. Means what does it mean amplifier? Means obviously here we are consider if we consider a signal, small signal, if we give it as an input, then we can have a amplified, means enlarged output at the output of this amplifier circuit. So in this case, uh, two things we have to consider. First thing, that we have to make sure the bias is in proper way. Means we have to consider the biasing in order to make it into active region. So that's why biasing is one of the most important thing. Depending on that, the transistor, in which region transistor will be there, that was decided, I think, if you can recall from previous class. Okay, so that's why let's say for this case, this is a circuit diagram for a common mode, common emitter mode amplifier. So as you can see, so these portions, apart from this capacitor, these things is in biasing. This portion that actually it is in voltage divider bias mode, you can say, and this capacitor and this resistor and this capacitor and this is load. So all these capacitor are due to that signal, AC signal, mm, and we do not want to interfere between AC and DC biasing. So that is why we have used this capacitor. So this is bypass capacitor and this is coupled capacitor, base coupled capacitor, and also this is for output terminal collector coupled capacitor. So basically, we want to block the means we do not want any kind of interference between the biasing source, that is purely DC, and this is signal, or you can say that is also one kind of source, AC source. So we make them distinguished. That's why this is the means this coupling capacitor are most important. But first of all, this RB1, RB2, and RE and RC, and this transistor and VCC, this is for biasing only. Okay. So in this case, as it is mentioned that it is only VCC, means positive voltage they have applied, and you can say negative terminal is connected to the ground. So now from there you can conclude that what kind of transistor it is. It is basically Npn transistor, right? So and you have applied a positive source to the N side, means collector side. So that's why you can directly say that the collector base junction is in reverse bias and the emitter base should be in forward bias. And is it in forward bias? That is why this common mode, common emitter one model is in active region. So you have to be conscious about this thing. Okay, and depending on this, means we have to consider the values of this capacitor value and all these voltage divider resistance value and this coupling value. So one more thing, means if we consider a capacitor, sorry, amplifier, if you think of an amplifier, then easily you can say it should amplify the signal. Whatever may be the signal, it should amplify it. But the thing is that whenever we are considering as means we are saying that it is a signal, means it is an AC signal. So we can means there is two specific property of a signal. That one is amplitude and other one is frequency. And other more one is there, means one more is there phase of that signal. But still you can say consider the major thing that we are right now bother about, that is that amplitude and that of frequency. So if you consider a amplifier, let's say with a gain, okay, I think you are familiar with the terminology gain. Gain means if you have applied a if you have applied a input and you are having some output, the ratio of means how much times you are having. Someone is unmuted, please. If you want to say something, say it, or else you can mute yourself. But once, who is this? Okay. If you want to say something, you can ask me at any point, but make sure unnecessary noise will interrupt all of us. That will. Okay. Anyway, so what we are discussing about that basic property of a signal, that is amplitude and frequency. So if you have applied, let's say a 50 hertz and 1 volt signal, that should be some depending on the gain value, gain factor. Gain means the ratio at which you will have a amplified version. So if you have applied a 1 volt, let's say, and the gain is 10, then you should have a 10 volt as the output. If you have applied the input of 1 volt and gain factor is 10, then you should have output voltage as 10 volt. So that's the simple meaning of gain. But the thing is that it is not all means it is not practically possible to design an amplifier which can amplify any signal. Any signal means irrespective of its frequency. So means whatever may be the frequency of that signal, if you have applied a our home appliance 50 hertz one, that will be amplified. If you have applied your mobile communication megahertz, sorry, means not megahertz, means megahertz signal also, terahertz signals also are there, gigahertz signals also there for different communication purpose. So if we want to have an amplifier for all this region or all these applications, it is not possible. So why so? Because there is a specific bandwidth. Means whenever we are trying to design any amplifier, it should have some specific bandwidth. What does it mean, bandwidth? Bandwidth means it will operate between a specific frequency region. Means it will amplify those signals, those who are in the in between these two frequency. Let's say for whatever we'll see actually basic motivation for our this experiment is to find the gain bandwidth one, means frequency versus a band. We have to find the bandwidth for amplification. So that's why I'm telling you all these things. So this is our motivation for this we have to design an amplifier, and from there we can see on which parameters means on or how we are having a bandwidth, means amplification in between two specific frequency region. Means if you have applied, let's consider this amplifier will operate from 10 hertz to 110 hertz, 100 kilohertz. Let's say 10 hertz to 110 kilohertz. So then the frequency range, this in between this frequency range, then bandwidth will be 110 kilohertz minus of 10 hertz, let's say. Or if you consider 10 kilohertz to 110 kilohertz, then the bandwidth will be 110 minus of 10 means 100 kilohertz. So that will be the bandwidth of this amplifier, specific amplifier. So we have to give numeric values for this, and depending on that we will have this, and also depending on the transistor characteristics. But still we can say that this means I think now the bandwidth, what is bandwidth, it is little bit clear to you. What does it mean bandwidth, and what does it mean gain, this terminology, and what is the amplifier basically. So in this case, we are having this amplifier, and also it will be means you can have you can explore this that audio amplifier that means you are using, or so many appliances are there. They are having audio amplifier, so you can design an audio amplifier that is also higher version for this one. But before going to that, you have to study this. So why I'm telling you audio, because you know, means we can hear something between a particular frequency range. So, and in that also there are so many regions. So if we want to amplify a specific thing, specific band, you have to design accordingly. So basically, that's the thing. Means this is our motivation for today. That for this common mode, common emitter mode amplifier, we have to find out the bandwidth of this amplifier, and at which this will operate basically. So basically, yeah. Any question? Someone want, if you have any question, you can ask me directly. We can discuss. Till now, any question? Yeah, you can ask. Means actually, I am introducing different terminology. Maybe some of you are aware of, but still, actually, I thought that we can discuss a little bit, then we can proceed. Till now, if you have any query, then you can ask, or else we can continue. You can ask me through chat also, and also unmute yourself, and you can ask. Anyone? Any question? Okay. I hope you are understanding, and if not, you can ask. And if you are not interested in asking, also, you can go through this all these details. Those are here in that VLab website, and also resources are given, references are given for that references. NPTEL lectures are also there, and books are there. So if you want to explore, you can go through all of them. Okay, so this is the thing actually we were talking about, the bandwidth of this amplifier. So this is if we plot the gain of this amplifier in dB scale. So are you aware of dB scale? What does it mean, dB? So anyone, if you are do you know what is dB represents for? Decibel basically, but still means, do you know this scale, specific scale? As you can see here, it is 20 log 10 A, that is in dB, that 3 dB deviation. So are you aware of these things? Anyone?
Sir, is decibel the logarithm of amplitude? Intensity.
Okay, so yeah, and so it's basically you can say it is another scale where you can represent, means scale down so many things. Means the higher value you can scale it down. Okay. So why it is important? Because let's say if our amplifier is having a gain of 1,000 or 100, okay, means what does it mean? If you have applied, let's say it is 1,000, then if you have applied 1 millivolt, then you should have a 1 volt at the output, right? So, and if let's say if you have applied some greater number in the input, then you should have some greater number at the output. So in order to suppress that things and also represent the same thing, the dB scale is required, means decibel scale is required. So in this case, in order to find the gain in terms of dB, we have to find the 20 log of A. A means basically output by input terms, means that gain in absolute scale. Let's say if we have means if we have applied applied 10 volt and we are having 20 volt as an output, so gain factor is 2. So then in dB scale it will be 20 log of 10 and 2 basically, means 20 divided by 10. So that will be around 6.02599. So in dB, this will be the value. And absolute value means in voltage scale, the value will be 20 volt and output voltage is 20 volt and input voltage is 10. Okay. So in this way, we can convert into dB scale. So here you can see that the bandwidth is measured between means 3 dB less to the maximum value. Means why it is considered as means this bandwidth measurement. What is the protocol for that? Means how you will find, means sometimes this is actually schematic. Sometimes you will have an again band, means then again plotting as some bell shape or something like that, means a Gaussian shape will be there. So at that case, how we will measure that frequency or bandwidth, lower frequency and higher frequency. So there is a standard rules is there that if the output means if the output is less than 1 or is 1 by root 2 times 1 by root 2 times of the maximum value, then we can say it is, means we can consider that particular frequency value. Means for this case, let's say this is A naught, means highest gain we can achieve. In dB, let's say it is 13 dB. And we have to consider to another point where it is having 10 dB, means less than the maximum value. Maximum value was 13 and we are having 10 dB and 10 dB at this particular two frequency. One is lower frequency and one is higher frequency. So difference between these two will act as an bandwidth of that particular amplifier. Is it some sort of clear to you how to find the bandwidth of an amplifier? Means how to find out the FL and FH, higher frequency and lower frequency, to measure the bandwidth. Is it some sort of clear to you? Or any doubt? If you have any, you can ask. Okay. I hope it is clear to all of you. Okay. So basically why, yeah, someone is asking that. Okay, thank you. So, and why this is 3 dB is coming? Let me show you how it is coming. Let's say your that the value, initial maximum value was A times, and now it is A by root 2 times, means A divided by root 2 around 1.4 something. So then the value will basically A maximum divided by A by root 2 will be, it is square root of 2, right? So it will be square root of 2. So basically we have to do 20 into log of square root of 2. I hope it is clear to you why we are doing square root of 2. Then you can say that it is almost 3, you can say. So that's why in dB scale, if the value is less than, means 3 dB less, at that point you have to consider. And in absolute scale, if the value is root 2 times, means initially if it is, let's say your gain is 2, and now, or 4, let's say, now at which point, means at this particular point, and this particular point, initially it was 4, and now at this point it will be 2 root 2, means because 4 divided by root 2 at this point also and this point also in absolute scale, and in log scale it will be 3 dB less. Anyway, so in this way we have to measure. So we have to consider the frequency V out and V in, and from there we have to find out the gain in dB scale. Then we can plot this one. So this is our motivation for today. So this is the simulator in VLab. After doing this, and we'll go to that, if time permits, to that circuit design one. Okay. So from the instruction, as you can see, we have to keep, means we have to choose the specific value, means we have to calculate the value of RC and or you can say coupling bypass capacitor, coupling collector capacitor, and coupling base capacitor. We have to calculate. So that's why one standard consideration is given. Why it is so? Because from here, as you can see, that this thing should be maintained, then only it will bypass. That we are considering this is a bypass filter. Means it bypass filter means it will pass the AC signal and it will block the DC signal, you can say. So in this case, bypass filter consideration should be like this, means the value of the capacitor should be very, very greater than that of 1 by 2 pi f. F is the frequency of that applied signal into Re. Re is this emitter resistance, this value. So that's why one standard value is given, instruction is given. So we have to keep the source at 50 millivolt 1 kilohertz. Is at 1 kilohertz, that is the source one, but the frequency we can change. Keeping the source voltage constant, vary the frequency from 50 hertz in a regular step. Okay, so let's change the value, means amplitude of that source as 50 millivolt. So we can change the value from here. So frequency we can change, and this is RS, yeah, depending on the RS value. Okay, so RS should be 100 ohm. So we cannot change it. Okay, we have to change it. RS should be 100 ohm. Okay, it is 100 ohm. Then RC should be 4 kilo ohm, and the emitter resistance should be 1 kilo ohm, and the load should be 2 kilo ohm. Okay, so collector resistor should be 4 kilo ohm. Collector resistor is this one, that should be 4 kilo ohm. It should be 4,000. So that's why we are keeping it in 4,000. Okay, and emitter one is 1 kilo ohm. Okay, maximum value 1 kilo ohm they are given, right? And RL should be 2 kilo ohm. RL should be 2 kilo ohm. You can change the RL, so that's why RL should be 2 kilo ohm. Good. Then that base resistor or voltage divider resistor, the B1 RB1 should be 47 kilo and RB2 should be 10 kilo. RB1 47 kilo, 47 kilo. So we are considering the standard value that was suggested by them. So that's why we have considered. So 47 kilo, and this one RB1 is 47 kilo, and RB2 is 10. RB2 is 10 kilo. It is 10 kilo. Now we have to give the value of all these capacitors. Okay, now the collector capacitor should be 10 microfarad, and capacitor CC2 should be 10 microfarad, and also okay, every capacitor is 10 microfarad. Good. So it is in microfarad, then it is 10 microfarad. This is also 10 microfarad. What it is now? This is 10 microfarad, and emitter cap 1 is also 10 microfarad. Okay. So now I think frequency. Okay, frequency that we have not considered. Frequency we have to change from 50 hertz to a regular step. Okay. Now let's add the table. Add this data to the table. Okay. Now you can see for this one. In this case, biasing is done, and frequency amplitude is given. For the signal is that 550 millivolt, and for this case 50 hertz, we are considering this output gain. This is the gain value in is magnitude in dB. Okay, whatever means we have to find out or plot that graph, gain bandwidth, you can say, and gain bandwidth graph we have to plot. So starting from 50 hertz, we can change the value in a regular fashion. Let's say 150, 152. Okay, then 250, or okay, 300. Okay, 318. And okay, as you can see in this case, the magnitude is increasing. 10 dB initially it was 10 dB, then 19 dB, 25 dB. So as we are increasing the frequency, the value magnitude is increasing. So at 1.6 kilohertz, the magnitude is 33 in dB scale. Okay. And also still it is increasing. Still it is increasing, as you can see its maximum value till now it is okay. For 12 kilohertz also the value is bit greater, means it is increasing but very slowly. As you can see here, it is almost no change, though we have changed the frequency from 12 kilohertz to 26 kilohertz, but still the frequency means change in magnitude is less. So from here also you can have an idea about this that plot nature of the curve you can have. So 60, okay, 503, still the value is increasing. Okay, now you can see, check. Now the magnitude is decreasing. So throughout the region, it was some means maintaining a fixed value, and then it is decreasing. So initially it was increasing. Basically, in practice, we will have a bell-shaped curve initially. Okay, let's plot them. Then we can. I hope. Oh, good, very good. So as you can see, the beautiful curve for the frequency response, the magnitude in dB, you can say, and this is a frequency. Obviously, the frequency scale, it is not linear. It is a semi-log or logarithmic plot. So that's why you can say after 100 hertz, it is showing 1 kilohertz, and then 10 kilohertz, then 100 kilohertz. So right now, I don't think we have semi-log graph paper. Means if I think you are familiar with semi-log graph paper. So actually, we were used to sorry, we were used to plot this frequency response curve in semi-log graph paper. So and the semi-log graph paper is something different with respect to that normal graph plotting. So basically, you can see that throughout this frequency region, the magnitude is fixed in dB scale, and it is decreasing again when we are increasing the frequency. And from here, we can calculate that maximum mid band gain and low frequency cutoff and high frequency cutoff. So all these are in hertz. So as you can see that high frequency cutoff is 2 into 10 power 7 hertz, means around 20 megahertz. And in this case, it is 5 kilohertz, more or less, means you can consider. So the bandwidth is starting from 5 kilohertz to 20 megahertz. So it's a huge bandwidth in this case for this application. But still, as you can explore further, that means we need more precise, specific amplifier for different amplification purpose. So as you can see, so this is that amplification portion, means common emitter amplifier one. So the thing is that in this case, we have considered all this suggested value. So if it in practice, you have to calculate, means you have to go through the process, means you have to go through the little bit theory from which this model is there. Different small signal analysis are also there. From there, you can find out what means you can initially calculate what will be the bandwidth, what will be the frequency, lower cutoff frequency, higher cutoff frequency. But in experiment, you have to consider that value of coupling capacitor and all this resistor value. You have to be conscious about that. Okay, so I think this is about that this one, that virtual lab one. So if you have any query, you can ask me, or else we can move forward to this one. Okay, yeah. Do you have any query? Anyone? Those who are online at least?
Excuse me, sir.
Yes, please.
So I'm asking that if we have to make all these circuit in the real life practical work.
Means I'm not getting practical work means.
Means if we are in the campus, then we have to prepare all these circuit.
Obviously, it is a regular thing. Means it was, I would like to say, it was a regular practice. So we have to design all this circuit in breadboard, and we have to analyze the frequency response and all these things with the help of CRO, DSO, and all these things.
Okay, sir. Thank you.
Okay, Hemant, thank you for asking this question. Okay, anyone, anything related to this virtual lab session that till now we have discussed? If you have any query, you can ask me. You can ask me directly, unmute yourself, or by chat. Through chat, you can ask. Okay, so I don't think that you are having query.
No, sir.
Okay. let's move forward. Means we can design this circuit here. It means initially, actually, it gives me the feeling. I want to share with you that this virtual lab, initially we are having two type of experimental setup. It's not in our lab, means I was studying. So basically one setup is that kit box will be there for any specific experiment, and you have to just connect the knobs and vary and take the data. That's it. So that was the that is similar for you people, that as you are online people, so this is similar for that kit experiment. So in this case everything is there, they have connected and they have given a values and all these things, and you just have to vary the frequency, means you have just vary the knob. And one was that is different, that was the breadboard one, means where you have to do connect all the components step by step, and each and everything you have to bother about, you have to consider. So that's why I think this is also one of the important thing, that online simulator, that is also one of the good aspect for you people. So and I think I don't know whether you will be you will have to give exam or not, means for this lab, maybe some quiz will be there, and if you want then you can at least do some project work or assignment type of things, not on basis of marks. It is completely depends on your interest. If you are interested, I can give you a different means one small project you can do, and you can simulate it here, and you can means submit it. It is there is no marks for that, means, or it is not mandatory, it is not under your curriculum, it is only for you if you want to explore it. That's it. Means circuit simulator one or electronics things, if you want to explore. Okay, so let us start this one. So basically we have to just a minute. Yeah, we have to draw this circuit, we have to design it is accordingly. How the two window is visible, right? Means I have splitted, one is multi-sim one and another one is that virtual lab. Both the circuits are visible, means both the windows are visible. Anyone please response, means these
Sir,
two
only
only.
this VLAB one is visible.
Okay, okay. Now I think it is visible, right? Yeah.
Now only multi-simulator.
Yeah. Okay. So we are going to design the multi-sim one. So as it will be similar to that of our virtual lab circuit. So that's why we're going. Okay. For that one, first of all, I think it will be better if we connect. We have to do step by step. First one is, means you can do accordingly, but still I think it will be a good practice if you just configure the, means bias the transistor first, means biasing circuit, then that amplification and signal portion. So for that one we need a transistor first. So Npn transistor we do need, and then we need couple of resistors, that we do not need to change the details. We need 4 resistors. So 2 resistor for, okay, all those are in vertical form. So let me rotate it and then copy. So 2 are for that base one voltage dividing circuit, and 2 for one for emitter and one for collector. So now let me connect them. So in this case, R1 and R3 are the base resistor, which was mentioned over the. Okay, let me rename them accordingly. This is RB1, base resistance 1, and this is R. Instead of R3, we can write it is base resistance 2, and the value also we can put here that it was 10 kilo, 10k. The RB2 was 10k and RB1 was 47k. So we are just considering the same value as we have done the circuit simulation in virtual lab, and now make them connected. Okay, and now as they are base resistors, so we are connecting the base. Okay. Now the collector one, we should rename it as RC. Then the value we have considered over there is 4 kilo, that is 4k, and the emitter resistor, that is RE, and that we have considered as it is 1k. Okay, no issue. Okay, then let's join them. We are going to apply same voltage, same source. Instead of connecting two different source, in this case we will give the source as a single source. So through a single source we are going to so let's add an ground. So as you can see that we have done with that resistive component elements along with the transistor. We have connected RB1, RB2, that is basically voltage divider bias we have given. So this is for voltage bias, biasing the base, and this is connected to the collector, that is, we have, it should be 4 kilo. It is 4 kilo. But is showing 14 kilo. Oh no, that is the line number. So it's not 14 kilo. Yeah. So connection, this line number, this is 1 and this is 4 kilo. That is different. Okay. And then what we have to do, we have to apply a VCC, means a positive voltage source. That is for biasing one. So this is DC voltage source we have to apply. Now let's rotate it because we have to connect the we have to connect the positive voltage for this one, means positive source to this terminal, and we can ground this. Okay, so as you can see, we have done with the biasing one. So now our transistor is in active region. How we can say, depending on the bias voltage, obviously. So how we can say it is in active region? For active, what is the condition? What was the condition for to be in active region? One of any one of the junctions should be in forward bias and any other should be in reverse bias. If both of them are in forward bias, then it would be in saturation, and if both of them are in reverse, then they will be in it will be in cutoff region. So as we want to have an amplifier, that's why we should operate this transistor in active region. So in order to be keep it is in active region, we have to make sure one junction should be forward, one should be reverse. So this is a NPN transistor that you can very easily identify by this notion that if you consider this is P, current is flowing from P to N, so that's why you can say NPN. Yes, this is analogous, so for remembering purpose. So this is NPN transistor. So then this N side is connected to the positive terminal. So basically, what does it mean? Means it is in reverse bias. And also this positive terminal is connected, means positive voltage is connected to the P1 or P side, you can say. And it is this N side is connected to ground. So that's why you can say this junction is in forward bias and this junction is in reverse bias. This means base emitter is in forward bias and collector is in reverse bias. So that's why I think we are done with the biasing one that we have done previously. But this special kind of configuration is there due to this. We want to bias it with a single source. Instead, initially what we were doing that we would have connected two different sources for two different connectors. Means for base emitter we have to add one source, and for collector we have to add another source. So, but in order to, as we know, means the in circuit part, main thing is that reduce complexity and reduce space. So that's why we can, if means this method is applied, we can use only one source. We can change the voltage afterwards. But the next thing is that we have to apply a signal. So if we want to apply a signal and we want, and that means AC. So we have to isolate it from this bias one. That this bias should not interfere that signal. So that's why what we have to do, we have to connect three capacitors. One is for base coupling, and other one is for collector coupling, and another one is for that emitter bypass, means emitter signal bypassing. So let me rotate this. So this is the circuit. I think no need to give you the explanation why we are doing this specific circuit, because as you can see, we have done the same. We are simulating the same circuit that we have used in VLab.
Sir, resistor for the base, sir, for limiting current in the base?
Yeah, this two?
No, sir, to the base, directly to the base. The empty
Okay,
one.
okay. This one means why
Yes,
we
sir.
have not connected this directly resistor to the base, right? That is your question. Yeah, is it your question or you want to ask something else?
Yes, sir. That was my question. I mean, should we limit the current there to?
Yes,
Because there,
exactly. You are absolutely right that it should limit the current. Actually, if you consider apart from this AC source, if we consider the biasing one, so through the base the current is coming through these resistors, right? Means this RB1 and RB2, they are taking part actually in order to limit the current of the base. Because of if you want to make sure the current flow in this circuit, apart from that signal one AC part, so these are limiting, this RB1 and RB2, this base resistance 1 and base resistance 2, they are limiting the current to the base. Okay,
okay, sir.
thank you for asking your question. Okay, next. Okay, what I was discussing, that we have to, in order to isolate the biasing DC, it should not from that AC source. We have connected these three resistors, three capacitor, and this is for bypass one. This is for coupling one. Coupling means let's say you have another stage amplifier, means two-stage amplifier. So in that case, the same circuit will be copied over here, and output of this output of this first stage will be act as input of second stage. So that's why these two are coupled. Means these two are basically coupling. This is coupling with the initial input or initial signal, whatever it is coming, and this one is the coupling will help to couple with the output one. So in this case, in our case, we are going to use load resistor, and in other so many cases we can have different kind of load, or maybe in second stage we can have same amplifier or something different amplifier. Okay, so let me make sure the correct circuit is in same manner. So now we are connecting this one. This is our RL. Rename it and give the value as. So this is our RL load resistor, and the value is 2000 ohm or 2K. Okay, so and I think all these are connected. This RL is connected to the ground. This resistor is also connected to the ground, and two things. Okay, and this should be the RS, source side resistance value. We can say that is very less. That's why 100 ohms. Okay, and it is connected to this capacitor. Then we have to have given frequency AC current. AC source. Okay. So sorry, what I have applied current source. Sorry, it should be voltage source. We cannot use this one. AC voltage we have to use, not AC current. Okay, so this is a voltage source, and this should be connected to the source resistor, and the another terminal of this voltage source should be connected to that of ground. Okay. So now I think we are done with that signal part, means that AC part. So initially, this was the DC part or biasing part, and now the capacitor one and these things with the source AC signal, that is with similar to that of, you can say, AC source. Okay, now what we can change this voltage to 500, 50 millivolt that we have used, right? It was 50 or 5 millivolt? 50 millivolt, I think. It is here. 50 millivolt, yeah. So we can use 50 millivolt. Now we will change, vary the signal, frequency of that signal, and we want to measure the voltage. As at this terminal, And also we want to measure the voltage. So it is not required input one, still okay. So we want to measure the input and output. So now instead of interactive one, what we will do, the AC sweep. AC sweep we will do, and for this AC sweep we have to set the frequency range for which we want to have. Okay, starting frequency should be, or let's say 50 hertz to 1 raised to 10. Okay, stop frequency we can limit it at 1 raised to 8 or 9, let's say. Okay, and points per decade is 10. Now I think we can run it and we can have a view of the output. Okay, so it is already there, but we do not want phase, only the magnitude one we need. Okay. And also the output one, it is required only. Now, till 1 gigahertz it is there, means it is not decreasing, but it should decrease. Zoom all. It is not running. We do not need phase, that's why we are interested in. So it should decrease. Why it is not decreasing? We should, I think we can you please remember that what was the bandwidth that we had there in virtual lab till 10 sorry 21 2 into 10 power 8 7 we did we have. So in this case it should be okay, maximum frequency. Yeah, so that's the thing we have to change. 1E8 and 1E8, then 1E9. Magnitude. Yeah, it should decrease, means as it is increasing it should decrease. I don't know why it is not decreasing to the desired value. Maximum frequency is 10. Okay, let me increase the frequency, then let's check. AC sweep is for AC sweep, this value is 10 power, let's say 12, and 10 points instead of 10 points, let's say 100 points. And let's run it. And yeah, with the AC sweep we can have that out, means exact waveform pattern that we saw in that virtual lab output one. I don't know why it is not decreasing. Magnitude should be in log scale. Yeah, we have done. Magnitude vertical scale in magnitude, that is in maximum 100 millivolt and maximum 100 volt logarithmic scale, not in linear scale. It should be in. Still, this end should decrease. Why it is not decreasing? I think that is due to the property of that transistor that we have considered over here. That may be considered that realistic one, not realistic one, ideal one. That's why maybe they have considered there is no such thing. But it should means ideally it is showing the ideal nature that increase there is no such particular finite bandwidth, you can say, but it should have some finite bandwidth. I don't know why it is not showing. Let me change the let me change it and check it whether it is working or not. Okay, this biasing that we have considered 5 volt, let it be in 1050 volt. It should be 12 volt or something. Consider 10 volt. Yeah, because biasing also one important thing, because the resistor values are high and that VLab one they have not given what should be that bias voltage for this specific one. Okay, actually it should come in this way, means it should be like this as well. Oh, sorry. I have not changed. Oh, sorry. I have considered another value for this one. It should be 10 microfarad that was used in virtual lab. Yeah, capacitors are the one of the key portion limiting. Yeah, I think due to capacitor we did not have this one. Let me try with the exact value. 10 microfarad they have used. Oh, no, still we are having the same issue. But in practice it should be that of it should decrease, means it should have finite bandwidth in practice. I don't know why it is not coming for this case. Let me try and then it is not. Till 1 terahertz it is not decreasing. Is there anything wrong that we have done? Let's consider the circuit. Okay. So we have considered RB1 47. Yes. The source voltage as 50 millivolt, 1 kilohertz frequency, and change from 50 hertz to a regular step. Okay, then RS value is 100 ohm, 100. Then RC is 4K. RC is 4K. Emitter RE is 1K. Yes, it is 1K. Then RL is 2K. RL is 2K. Okay. Then base resistance 1, RB1 is 47K, and base resistance 2 is 10K. Okay, it is 10K, and all the capacitor are in 10 microfarad. Yes, all of them are in 10 microfarad, C1, C2, C3. Okay. And what is the problem? Maybe we are having the interactive one. So if we can change the value directly, then let me check whether it is working or not. Why we are having this clamped one? So it's 50 milliamps. We are having a nature as because we have given 5 millivolt and we are having output of 35, something like that. Yeah, 33 or 34 millivolt. Yeah. Now in this case, this is the input signal and this is the output signal. So, okay, one more. Yeah, this is also one of the important thing that you can visualize from here. That the green one is the outputs waveform, and a blue one is that input waveform. So from here you can see that it without any doubt the signal is amplified without any doubt, and it depends how much time. So if you consider roughly the input is 5 millivolt and the output is roughly 35, let's consider 35. So it is around 7 times increasing, means 7 times increasing. Now we can see. And one more important aspect is that I think I told you people that in this case collector current is in out of phase in common mode amplifier, means common emitter one. So as you can see, our output is completely 180 out of phase with respect to that of our input signal. So that this is also one of the property that you will have in this common mode one. We have already discussed. So now you can visualize it. Now we have applied a pure AC signal to this biased circuit, common emitter one, and it is amplified. Now I think we can stop it, and I think we will have a proper AC sweep. Okay, and for AC sweep, I think it will take the automatic value, and we will have the exact bandwidth nature. Means again, still we are not having that exact nature. I don't know why it is happening in this way. Basically, it is frequency response. AC sweep basically frequency response. It will show the magnitude of that output signals in this case, and as well as if we want to have the input signal. So basically, gain is that ratio between these two, maximum of this output and input signal. Okay, then go back to that interactive one, and let's change the value one by one. Means let's change the frequency of it. So then I think we can have this one. Okay. This much of gain. Now, if we increase the frequency or decrease the frequency, just as we increasing frequency, that I think due to the capacitor resistance value, we are not having the pure AC signal. That is maybe the one of the reason. I don't know why it is not coming. Okay, let me change furthermore. Now the sorry, why we are increasing voltage? I should increase the frequency. I'm sorry. Now let's change the frequency. Let's say it is 10 kilohertz. Still not affected. 1 megahertz not affected. 1 gigahertz not affected. 10 gigahertz. 1 terahertz. 10 terahertz. 100 terahertz. No. I don't know why it is not. Why it is behaving like that. It should not be the case. So we should have a vary in amplitude value. Okay, let's change the input frequency. If we decrease it, still it is not varying. I don't know. Maybe due to some mistake or some problem we are doing. Due to that, we are not having this exact waveform pattern. But it should be like this. Okay. Anyway, I think this is the complete nature. Means this is the complete diagram, but I don't know. Maybe due to that selection of the transistor that we have to consider. But all this value we have considered from VLAB only, apart from VCC. VCC value it was not there, but consider all this value. Anyway, okay, I will try to figure it out and tell you people on next lab. But the thing is that I think you have little bit understood about that basic nature of that amplifier, how it is working basically, and what is the gain bandwidth. Gain versus frequency plot for an amplifier, common emitter amplifier. So basically, we were searching for this output, means this type of nature. That output, yes, this type of frequency response we should have, but I don't know why in this simulator we are not having that or AC signal or AC response. it should be like this. Then we can calculate this bandwidth and also this higher frequency and lower frequency. Anyway, so I think you have little bit idea on this one, and I'll try to figure it out if I can find any problem why it is not working. Also, if people try, if you find, please let me know, and also if I can find, then I'll let you know. But it should be like this. It is not like that. It is infinite bandwidth. It is not possible. Ideally, it is possible to have infinite bandwidth, but practically it is not possible. Okay. So till now, if you have any question, please ask. Then we can conclude our today's session. So anyone, do you have any query? Or if you cannot understand something that we should be discussed, means then I can discuss it. Or else if you have any other query also related to this lab, you can ask. Okay, at least those who are online, please respond if you have any query, or if you are unable to understand anything, then we can discuss, or else we can conclude. Okay, I hope you people are not having any query. So if you have,
So once we will try on our own. If we have, we will ask in the next lab.
okay, sure. Try. You should try it on your own through this multisim. Then it will be very. If you have any query, you can ask me directly on next lab or through mails, or we are here to help you out. Okay. Thank you. Thank you for
Okay, sir.
attending this
Thank
session.
you.